Hey everyone, I'm Val, and this is my video abstract for my thesis entitled Gravitational-wave-induced oscillations of a viscoelastic sphere. General relativity predicts the existence of gravitational waves, which are usually generated by accelerating relativistic objects, such as binary black holes and binary neutron stars. A gravitational wave signal from binary systems, which can be detected by detectors like LIGO, contain information about the masses of the component objects, the mass of the remnant object, and the distance away from Earth. But before our current interferometry-based detectors were conceptualized and eventually built, the first detector was made by Joseph Weber. His 3-ton detector, called the Weber bar, was an aluminum cylindrical bar with piezoelectric crystals attached to the surface. The Weber bar vibrates only when the frequency of the gravitational wave is almost equal to the bar's natural frequency. The basis of my research is the paper by Siegel and Roth, in which they treat a solar-like star as a gigantic spherical gravitational wave detector. This was motivated by the fact that gravitational waves cause objects to vibrate. Since the induced deformations are small, this means that we can model the vibrations using the theory of elasticity. The focus of my thesis is the Q factor of the normal modes, which tells us how good the sphere oscillates when it is being impinged by gravitational waves. Numerical results show that the Q factor is highest in the first few quadrupolar mode, and that the Q factor is sensitive to the radius of the detector. A natural extension to Siegel and Roth's model is the dual sphere, which is composed of two layers with different material properties. To build the dual sphere model, we solve the same equations as before but impose extra boundary conditions. Results show that a dual sphere's Q factor exhibits an amplification as compared to a solid sphere of the same radius, as indicated by the plot to the left. In the plot to the right, it shows that an equally sized dual sphere has a much higher Q factor, and the natural frequencies of the normal modes occupy the 200 to 10,000 Hz range. This effectively makes a sufficiently sized dual sphere a good complement to LIGO. For a more complete discussion, I would like to invite you to my thesis defense, which will be held on August 10 at 3:30 to 5 p.m. in Zoom. Please register using the QR code below. See you there.